Hello and welcome to the New Mexico Geochronology Research Laboratory. It's a pleasure to be part of Earth Science this week and working with the Grand Canyon GeoFest. I'm Matt Heizler and I'm the director of the New Mexico Geochronology Research Lab. This lab is the brainchild of Chuck Chapin, a former director of the Bureau of Geology, and my longtime co-director Bill McIntosh. The New Mexico Bureau of Geology is the state geological survey, and we're a research division of New Mexico Tech. So the potassium-argon dating geochronology method is based on the natural radioactive decay of potassium-40 to the argon isotope, or the daughter isotope argon-40, with a half-life of about 1.25 billion years. That is about 1/4 of the age of our Earth. So in this laboratory we specialize in measuring the argon isotopes from a variety of potassium-bearing minerals. And potassium-bearing minerals occur in all geologic environments, and therefore the argon, or the potassium-argon geochronology method, is of high utility to the geosciences and has played a key role in understanding the geologic evolution of the Grand Canyon region. So I'd like to introduce you to some of the equipment and some of the things that we do. The first thing we have to do is remove minerals from our rocks. So a typical rock, I'm sure you've seen, this is for instance a granite, and it has multiple minerals in it. And in this case it has 3 potassium-bearing minerals, 2 micas and a potassium feldspar. So when we take this rock and we grind it up, and we use physical properties such as density and magnetism, and we separate the minerals, and we end up with little vials of feldspar or micas or amphiboles, and these minerals are the ones that we're going to try to date. Because our laboratory is only designed to measure argon, we have to do a little trick to measure the potassium of our sample. And so we send our samples to a nuclear reactor, and we change some of the potassium into another argon isotope called argon-39. So if we measure the daughter product argon-40, and we measure argon-39 as a proxy for the parent isotope, the 40 to 39 ratio then becomes a measure of the rock's age. So let's introduce you to another aspect of what we need to do, and that is to measure the argon isotopes. And one of the big challenges of that is there's a lot of argon in the atmosphere that you're breathing. In fact, argon is the 3rd most abundant gas in the atmosphere, behind only nitrogen and oxygen. And so a tiniest bit of atmosphere in our sample causes us a lot of difficulty in measuring the argon in our rocks and minerals. So in order to overcome that, we have to build an ultra-high vacuum sample chamber. And so when we get our samples back from the nuclear reactor, we commonly put them in a little holder such as this, and then that holder goes into a stainless steel flange. And to make the gasket, to make the vacuum seal, we use a copper gasket in this case, and we sandwich that gasket into another, between another flange. And in this case, this flange has a window such that we can fire a laser through this window and melt our crystals. And I'll show you how we do that in a little bit. So again, the challenge is measuring the argon in our sample, and we are fortunate to have 2 mass spectrometers to do that. And I'm going to walk over here and just introduce you to our mass spectrometers. This is our mass spectrometer, Felix. And Felix is a big guy, okay? And he specializes in what we call high-resolution mass spectrometry. And I won't go into the details of that, but Felix I'll contrast with Jan, who is over here. So Jan, she's tiny and petite, and she is incredibly sensitive. And so Jan is best suited for measuring very tiny amounts of argon, or in this case, we describe measuring very small pressures of gas. Okay, so let's ask ourselves, what is a tiny amount of argon pressure? And I like to connect it to something that people are familiar with, like a tire in a car. And I think we all know that the pressure of a tire is about 32 psi. But let's ask ourselves what the pressure inside of a crystal is. And I want you to help me here. So the pressure in a crystal is about 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2 psi. I think you'd agree with me that that's a small number, but we can actually measure that very precisely and accurate in our lab. So let's walk over here and actually melt the crystal and see how the process works. So this is a camera view of this tray that I showed you earlier, and it's under vacuum now, and it has some crystals in it. You can see it takes a lot of computers to measure the age of a rock. We'll wake these guys up and see what they're doing. Okay. My colleague Jake Ross is responsible for writing all the software that runs this laboratory. It's quite an amazing product. So I'm going to set up an experiment, and I'm going to ask the computer to go melt the crystal and extract the argon from it. We'll see if it works. Seems like when we do these demonstrations, it commonly gives us a little trouble. So it has to do a little initiation, but essentially what's going to happen is this video will show the moving of the laser as it goes to the pre-described crystal that we're interested in melting. So it's traveling to a hole that I've pre-programmed that has a crystal in it, and it's going to do a little positioning of that sample based on image analysis. Looks like it's almost ready to begin the lasing. So that poor little crystal is now being melted by the laser, and argon is being extracted amongst other gases. We will clean those gases from the sample, and then this gas will eventually flood its way into JAN for isotope analysis. So in about a minute or so, the gas will flood into the mass spectrometer and will be measured for its isotopic composition, and we will be able to know the crystal's age. So I hope that was helpful, and I'm looking forward to seeing you in the outcrop. Thank you very much.